All right, today we're going deep, really deep, underground, to figure out the incredible science that keeps millions of tons of rock from, well, collapsing on top of us. So what's the secret to holding back the Earth itself? Let's dig in.
If you've ever been driving through a tunnel, I bet this exact thought has crossed your mind. You're literally surrounded by a mountain. The secret to making sure it all stays up isn't just about digging a hole. It's about actively fighting against the immense and frankly unpredictable pressure of the ground itself.
And that right there is the heart of the problem for every single tunnel engineer. The ground, it's a dangerously fickle partner. You have to work with it, but man, you can never fully trust it.
I mean, just imagine trying to build anything when the very foundation you're working on changes every few feet without warning. One minute, you're drilling through rock that's as solid as it gets, and the next, bam, you hit a pocket of fractured, weak junk, or even something that acts more like loose dirt. This constant change is the single biggest headache in tunneling.
So how in the world do you deal with that? Well, engineers don't just wing it. They use a really precise three-step scientific process. First, they analyze the ground like a detective at a crime scene. Second, they classify what they find into different categories. And third, they prescribe the perfect support system for that specific condition. This whole process is the absolute key to building safe tunnels.
So, let's dive into that first step, the diagnosis. This is where geologists basically put on their detective hats. They're reading clues hidden deep within the earth to figure out exactly how the ground is going to behave once you start carving a tunnel through it.
The first big clue they look for is something called lithology. And that's really just a fancy word for what the rock is actually made of. Are we talking about something like granitic gneiss, which is this massive, super strong type of rock? Or is it something like phyllite or schist, which are known to be kind of weak, flaky, and love to buckle under pressure? The type of rock itself tells you its basic strength.
But what the rock is made of is only half the story. The other crucial piece of the puzzle is its structure. Is the rock one single solid block? Or is it a shattered mess, just full of fractures and cracks and joints? Because a solid block of even a weaker rock can actually be more stable than a fractured block of a strong one. It's all about how well it holds together.
And this slide right here, it just perfectly captures the two extremes. On the left, that's the dream scenario for an engineer: solid, stable, predictable rock. On the right, that's the nightmare: a loose, messy jumble of boulders and dirt called colluvium. Trying to tunnel through that stuff is less like drilling and more like trying to dig a hole in a wet pile of sand.
All right, so once the geologists have done their detective work, it's time for the engineers to write the prescription. And they have a whole toolkit of different support systems designed to handle every condition you can imagine, from the best rock all the way to the absolute worst.
So here's a look at some of the heavy hitters in that toolkit. You've got shotcrete, rock bolts, wire mesh, forepoling, and steel ribs. Now each one of these has a very specific job. And the real magic is how they're used together to create a custom-fit solution for whatever the ground throws at them.
Okay, first up we've got shotcrete. The easiest way to think about this is like an instant protective skin. As soon as a section of the tunnel is dug out, a layer of concrete gets sprayed right onto the exposed rock. This stops little pieces from flaking off and basically seals the surface, stabilizing the opening right away.
Then you have rock bolts, and these are really clever. They show how engineers work with the rock, not just against it. These are long steel rods that get drilled deep into the rock around the tunnel. They act like stitches, literally pinning unstable chunks of rock back to the more solid stuff behind them. It basically knits the whole fractured area together into one reinforced arch of rock.
But what about when the ground is just a mess? I mean, when it has practically zero strength on its own. That's when engineers bring out the big guns: massive steel ribs. These things form a powerful steel skeleton inside the tunnel, and they take on the load of the earth directly. This is the heavy-duty solution for when the ground itself just can't be trusted to do any of the work.
So, you see, the real genius here is in how all these different tools get combined. Let's take a look at how the support plan has to change, sometimes dramatically, depending on that geological diagnosis we talked about.
All right, so let's say you're dealing with good, solid rock. The approach is super efficient, almost minimalist. You can excavate a full 2 meters in one go, and the support you need is pretty light, just a thin layer of that shotcrete and some relatively short rock bolts. It's a clean, fast process.
But watch what happens when we hit poorer rock. Suddenly, progress slows down to just 1.5 meters, and the support system gets way more robust.
You need thicker shotcrete, now with wire mesh inside for extra strength. The rock bolts are twice as long, trying to reach deeper into more stable ground. And you even have to pre-support the ground with things like forepulling before you even dig.
And then you get this, the absolute toughest scenario, soil-like conditions. Progress now slows to a crawl, just 75 centimeters per cycle. Before any digging even happens, a pipe roof of long steel tubes is drilled over the top of the tunnel, kind of like a protective umbrella. Then, those heavy steel ribs go in immediately. Concrete panels are placed behind them, and everything is filled in. It's an incredibly intense, painstaking process, but it's exactly what's needed to get through the weakest ground safely.
So when you pull back and look at the big picture, you realize that modern tunneling is really this dynamic conversation between the engineers and the Earth itself.
It's like the ground says, here's my condition, and the engineers respond with, okay, here's the exact right medicine to keep you stable. It's this constant cycle of analysis and response, meter by painstaking meter. That's really the fundamental idea of modern tunneling.
And honestly, this chart just says it all, doesn't it? The quality of the rock directly controls how fast you can go. You can literally see how moving from good rock to poor rock and then to that soil-like stuff just dramatically cuts down how far you can safely dig in a single go. The engineering makes it possible to keep going, but it's the geology that sets the pace.
And look, this isn't just some textbook theory. This is the exact science being used right now to build massive projects, like the new railway line tunneling through Taranga Hill in India. This meticulous, data-driven approach is what makes these amazing feats of engineering possible and, most importantly, safe.
So, really, the next time you drive through a tunnel, you'll know it's not just an empty space. It's this carefully engineered structure that's actively holding the Earth at bay. And it makes you wonder, as we keep building bigger and digging deeper than ever before, what new challenges are just waiting for us, hidden right beneath our feet?